So we can't just come in and waste our time. So, test. Put in your diary. Week 10. We're going to look at our investigation, and the first part of it is going to be due Monday, week 9. On the positive side, we have pretty much had a look at, dip the finger in with principles, first principles. We've covered that. We've looked at doing the differentiation rules, yes? We just said simplifying first using your index laws. You didn't like that, Lorenz, but let's make sure we can do that. Making sure you can find the equation of tangent of the normal. Now, there's basic ones, right? Differentiate, you get the slope. But then there were some of those funky ones where it didn't give you all the information. It had some A's and B's involved. I reckon you could be guaranteed some of that stuff. Then we need to know, when is a function increasing, decreasing? That's all about, derivative. When is it positive? When is it negative? Yeah? Sign diagram. And then the thing that we're looking at last was the stationary points to sketch. So that's our plan. The thing that we want to do today is a last thing, which is optimization, and we made a decision yesterday that we won't put the optimization in the test because your investigation is basically going to be on optimization, okay? So, but we still have to cover that today, and you think, oh my God, is that new? No, nothing new here, because if you think about your stationary point, we have got, if you're looking at a graph, whoop, your optimum points are where? Right, optimum here, optimum here. Even though it's a minimum, it's still an optimum situation, because imagine if you're looking at, you want to get the best option for lowest price of something. That's going to be the best thing to do. You want the lowest, you don't want the highest thing. That's not good, that's not optimum, that's going to lose out on things. So really all we have to do is we will get an equation. How are we going to find the optimum, the max or the min? We will, say it with me. Oh, they're not saying anything. How do we find a maximum and a minimum without graphing? We find the stationary point. And how do we find the stationary point? Determine what's equal to 0? The derivative, right? So nothing new here, except it might be an equation now that isn't just y equals or f of x. It might be h of t equals. It might be SA of t, which stands for surface area. Your investigation is going to be all about maximizing the volume of a box. Right? I think, Dylan, you already started. There was one where it's maximizing the profit from a business. The difficulty is going to be, well, sometimes that will give you the equation, and sometimes you have to do a little bit of work to actually get the equation. All right? So that's where we're heading. Let's have a look. So as we said, the actual calculus that you're going to do, I don't think anything new to see. Hello? And if you had not actually finished the previous applications, you are going to be fine with this. Trust is a must. All right? With worded questions, you have to, if you aren't given the diagram, draw one. If you're not given the equation, draw one to get the diagram. You can read those steps. It's just sensible. This is basically your investigation. All right? If you're playing at home, you can't see, but I'm holding this up. Can you see that? If you want to see what I'm holding up at home, open up the investigation on OneNote. So let's have a look, and we'll do this without looking at the example of the solutions and see how far we can get. Because you will basically do this for the first part. All right, so heading. All right, we've got a rectangular cake dish. It's made by cutting out squares from the corners of the corners. And we want to find what size squares must be cut out to produce the cake dish with maximum volume. That is the key here when it says maximum volume, because that means we need to find an expression that is f of x equals blah, 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 because that's what we want to differentiate. Does that make sense? At the moment, all I know about volume is that it's length times width times depth. And this is no good to us because we've got 1, 2, 3 unknowns. So with every equation that you end up getting, you only want to have one unknown. They all need to be x's. So we're going to write it in terms of x. Yep. So let's go back and see what have we actually got here and where can we use our x's. And does everyone understand how that box is made, or do you need a visual demonstration? We're all good? Okay, so what can we do? The tin plate is 25 by, so the whole thing, what's that whole length? 40. What's this whole length? 25. And then they've cut out these little corners. Do we know how much they've cut out? I'm about to do a visual, so you're not going to see that at home. Oh, you missed out on a good thing. We just did some cutting. So, oh, that didn't sound good if I said that. Cutting of paper. Right, so we're cutting out X centimetres here, X centimetres there. So now, what would you call your new width? Oops, shouldn't have put that there. What is our width of the box? That width. Yes.
25 minus 2x.
It is 25 minus 2x. And he set the scene because then what would we have as this length here? Wait.
40 minus 2x.
Correct. And of course, what is our depth? What was our depth every time we cut out the x? It is the x, that's right. That's your x. So there we have our equation. And that is what we have to differentiate. Now, we can't differentiate it in that form, can we? We're going to have to expand it. Do it. Expand. So we're just talking about there's expanding brackets calculators. Now, I obviously think that you should be able to expand without using this because you will have to do things like that in your test. And you can't access this on the, but in your investigation, you're going to be doing a lot of expanding. So try and mix it up. And if you want to check, hells, bells, use this stuff, not bad. But remember, you don't have it in the test and you should be able to expand quickly. That shouldn't be the thing that slows you down. So I will not use it, except I don't know what 25 times 40 is. Anybody? Is it? Oh, I should have known. Oh, yes, of course. 25 times 4 is 100, 1,000. Well, that's embarrassing. So I would say this is the only new bit, is getting the equation. The rest you have done and dusted. Oh, actually, one other little thing. You will now do the derivative. You'll solve for the derivative. The one thing that's a little bit new is because this represents the volume, we have got some limitations on the values of x. Why must x be positive? Okay, so we have can we just all listen? Can I interrupt you for a moment? We need to make sure, yes, x has to be greater than, or, well, I'm going to say greater than 0 because if it equals 0, then it's a flat tin plate. Tom, you listening? Please listen to this. So we've got that. Is there any other thing that we have to worry about? Right, you cannot cut. If I go back to my bit of paper, I can't cut that square more than halfway through, correct? So if we're looking at this side here, we know that x would have, this side, we know that x would have to be less than 20. But of course, look at the shorter side. We know that x would have to be less than half of 25. Yep, so I'm going to just put half of that, and you know that that's half of 25. So we have this constraint that x has to be greater than 0, but less than or equal to 25 over 2. So when you do your sign diagram, right, we already know we're going to have a bit of a block out from 0, and we're also going to have a block out from 25 over 2. So 2 new things, getting the equation, making sure that you consider the constraints and the limitations of your values. Like if you did surface area, again, measurements, you can't have negative measurements. If you're talking about time, you couldn't have negative time. So look at each question, okay? If I had a company, could I have negative profit? Yeah. Yes, it's a loss. Then we cry. So it's not always has to be positive. Go, you good thing. Just about to say, do you need me to finish? But the example is in the book, but then they said, yes, finish it. So here we go. We will differentiate v dashed of x equals 12x squared minus 260x plus 1000. Okay. Oof. Now, someone just said, ow, can I factorize this? I wouldn't, because the numbers are so mighty. Mighty, mighty, mighty. One of the things I would do is see, is there a common factor? Because I'm probably going to go quad formula. But I'll use my technology to tell me if I'm going to factorize or not. So does 4, no, 4 doesn't go into those. So 2? 4 does. Oh, okay. That's me. So what says 4 the highest common factor? Okay, beautiful. So we've got 4, 3x squared minus, who can tell me? 65 plus 25. So this is, am I going to try and factorize or am I going to quad formula? I go to my calculator. I go down. We go equation. And we're talking about this for your investigation as well, although if you've already read it, it does say use the quad formula. So we go degree 2, 3 minus 65, 250. 3 minus 65, 250. Oh, look at that. So we can factorize. So how do I do this? 5 is going to be one of my values, and 50 over 3. Exactly, 3x minus 50 is the other one. So if we've got 3x minus 50 there, so can you see how you can use your calculator to help you work backwards? And x, of course. Take 5 and do a double check, 50 times minus 5. Do you know what I would also do? I would do a double check and go back and pop my original into the calculator to make sure that I pulled the common factor out properly. Right? I do not trust myself with these sorts of things. So use your technology to prevent you from making silly errors. Okay, so that means 50 over 3 and x equals 5. Now 50 over 3 is 16.6. That is going to be beyond. So we can't count that one. The only one we can count is 5. Oh, come on. Is 5. So pop the 5 in there, figure out how it's going, and to double check that you're okay, thanks, to double check that you're okay, graph this, G-solve max. And we should get 5 something, all right? Does that make sense to you all? Nobody responded. Yes. Okay, so because this is a single lesson, I want you to be able to work on your investigation over the weekend and catch up for any of the other stuff that we've done. We're not going to now look at any of the other optimization until next week. Thursday when I see you again. My God. Please, I would expect that you should be able to do all of part A, and that is the minimum that is going to be due Monday week 9, written up and everything. Typed. Perfect. But don't dilly-dally. You should be able to get most of it done by the end of this lesson. If you've read on in the investigation, what you have to end up doing is finding a conjecture. Now, to get a conjecture, another word, I hate how everyone keeps saying conjecture, conjecture. It's just another word for, anybody? a pattern, right? Anything that's just, you've got, oh, look, there's a link here. There's a pattern going on. So what you are doing is we're going to have a value for L, not 1. And the first one that they got you to do, it was 5 centimeters. And where did your max occur? And your max occurred when it was 5/6. You then have to choose at least 3 more values for L. Now, don't set them all to begin with. I would say maybe choose your next one. I suggested to the girls 30. Try 30 and see what happens. Then choose another. You don't have to do like, don't everybody do 30. So maybe someone else could do 20, or you could do 25, right? Do 30. Don't then go 30, 40, 50. You want to mix it up a little bit. If you've gone 30, you see something, maybe then go, oh, maybe choose and don't do another 5 one. What if we went, I don't know, 44 or 26? Do you get, you change it up a little bit? And then you're going to observe what is the connection. And you should end up with finding a connection / a pattern. And so then you could finish it off, and your conjecture will be down here that when you have any length, your value, your max will be I mean, already we can see something going on here. Will it be that you end up with 30/6? Like, will that happen? Who knows? I might be leading you up the garden path. But that's how you see the pattern easily, and I would include the table in your write-up. Capiche?